Okay, thanks for having me. Today I'm going to be talking about singular learning theory and trying to apply it to a toy model, which we're going to renormalize using Bayesian renormalisation. Just a quick sense of the room. Who here's heard of like singular learning theory before? Okay, that's pretty good. What about Bayesian renormalisation? Yeah, also pretty good. All right, cool. It's a home game. So the goals for today are we're going to ask the question, can SLT say anything about Bayesian renormalisation as it currently exists in a concrete setting? And one thing we usually want to do is we want to be able to compute asymptotic expansions of observables. So think like expectation values against your Bayesian posterior. And we're going to be working in the large data set size limit for this talk. The answer is yes, we can do this. Now, does Bayesian renormalisation as it currently exists preserve these expansions? The answer is not really. Some to leading order, but a lot of the observables you would want to be preserved seem to not be. And then the real question is, can we make some changes to try address this problem? This is very close to me. And the answer is yes, if we make some strong assumptions on our model. So that's what we're going to go through today. Hopefully we can answer it. So just a quick perspective on why I personally care about singularities. In classical learning theory, models are regular, which means that you can approximate them locally in their loss landscape by a quadratic form. But neural networks are a subclass of models I'm going to call singular, which means that their Fisher information matrix has a zero determinant, and also the parameter to function map is not injective. Now, the famous quote from Watanabe, the founder of SLT, is that knowledge to be discovered from examples corresponds to a singularity. That's quite a mysterious statement. I'm going to explain a bit more intuitively what that means in a second, right after I define what a singularity is in this context. And so we want to sort of study the structure of these singularities and hope to get some inference on the structure of that knowledge. So we have this like picture where network computation corresponds to the singularities in the loss landscape. So in other words, the geometry of the loss landscape near a trained parameter should correspond to the computational structure of your model. Now, I personally think if Bayesian renormalisation kind of destroys this singular structure, that can maybe inherit a generalization cost, because the SLT answer is that singularities help you generalize. So what is a singularity? I'm going to say this word a lot today. You can think of it as more than one geometrically distinct way to represent the same information. So in ahead, you can have a picture of a regular model, looks like a bowl with a single point at the bottom. And then like a singular model, this is like a normal crossing singularity, where you have two different zero loss axes that cross at the middle. And so just to answer the question before I asked of why would you expect singularities to correspond to knowledge? So now we know a singularity is more than one way to represent the same information. Informally, think of like when you were back in undergrad and you were stuck on a problem and you asked your friend for help, and they just sort of like gave you like permutations of like what the lecture slides say. It's like one answer, but they're like saying it in the same way with different words, and you don't really get it. Then you go to your lecturer and they explain it in like truly different ways, and then finally you like understand what the problem was. And this is sort of my personal feel for why singularities, meaning if I can explain information in many different distinct ways, then I understand it better.
Wait, I'm a little lost.
Yep.
And in fact, maybe that explains to me in several distinct ways.
Yep.
Okay, so first, what do you mean geometrically distinct? Like, I get this sort of that there's a parameter degeneracy, there's a
Yeah.
non-manifold subset of parameter space that represents.
No, that's a good question, and hence the asterisk, because I'm kind of being a bit vague when I say that. But you can think of these two crossing lines here as two different geometrically distinct ways to achieve zero loss in this picture. So when you've got say a population loss and you want to find the zero where it equals zero, the resolution of singularities theorem lets you write it as a product of monomials. So you've got a product of different functions which all can equal zero, and then where each of those components can equal 0, this is what I'm referring to as the different ways you can achieve 0. So like on an xy plane, for example, you could be along the x-axis or along the y-axis. Or in like a 3D plane, you could be in like the z-axis or the y-axis.
Okay, so then your intuition is like, the minimum in this direction is sort of like makes sense in way A, and the minimum in this direction sort of makes sense in way B, and then...
Yeah, that's like my personal feel. Yeah, that's right.
Yeah, and then this intersection point is sort of like...
Yeah, maybe that's...
the simplest way of thinking about the knowledge because it makes sense from both views.
Yeah, maybe. This is sort of like my headcanon, I would say.
Does Watanabe have like a more concrete...
Watanabe is famous for not giving a lot of intuition in his textbooks, in my opinion. I'm sure he has a good answer if you were to ask him personally, but he doesn't publish it. Okay, so thanks for the question. Ask lots of questions. I'm aware this is probably quite new to a few in the audience, but for now we'll just do a quick recap of like what the Bayesian setting is. So we're going to assume there's a given data set of IID random variables, and we'll be in the supervised learning case, and then we're going to assume that this data set came from a true distribution called Q, and so we want to learn this distribution that relates the input data to the output data. And we're going to fit to this data with a neural network, which I'm going to denote phi sub w, where w is our network parameter. And we can think of these as like functions from parameter space and input space to output. And then we're going to approximate this distribution with a statistical model called P. And this is just like a standard regression model where we take the mean squared loss of the output data set from our neural network, and then we generate a probability distribution. And so we want to try to fit this model P to the truth Q that generated the data set. And because we need to pick some parameters to start the whole process, we're going to define a prior distribution over our parameter space. And throughout the parameter space will be compact and finite. So the networks will be all finite dimensional, no infinite width limits here. Okay, so like I just alluded to, we're going to measure how good our model is against the truth via the Taylor divergence. So when k of w equals 0, that means that our model has perfectly matched the true distribution. In practice, we don't actually have access to the Taylor divergence. We have access to the something like the mean squared error loss or the negative log likelihood, and then we try to maximize something called the Bayesian posterior. So you can look at this distribution. This will be largest when ln of w is smallest as n gets larger. And then one of the central objects is the partition function, which is the normalizing constant on the Bayesian posterior. And we want to understand how this object behaves as the data set gets large. So here is one of the main theorems of SLT, where you've got this partition function, and then as n gets large, we can see that, oh, sorry, there should be an n in there. Let me just do that. There we go. So you get exponential suppression if you achieve the correct minimum loss. And then we also have these polynomial exponent and this logarithmic term. And then this lambda and this m will be some of the main quantities that SLT talks about. And then we have some random process that converges to a Gaussian process in the constant out the front. I just realized I should remove that negative n. There we go. Okay, so the state of the art so far is we can take the partition function's first order expansion, and we would like to also be able to consider expansions of observables, which I will think of as real analytic functions on our parameter space. Can be whatever you like. So one of the main results across my PhD is deriving a recursion formula for the coefficients that appear in this expansion. So we've always known that an expansion like this must exist, but now we actually have a way to not just get the leading order term, but also get all the lower order exponents and also the coefficients defined recursively. And these are all defined as like fluctuation integrals and their moments for lower order terms. So using this result, we're going to try to see what we can say about Bayesian renormalization. Cool. All right. What is this? So Bayesian renormalization is a way of pruning parameters in your model, and then you want to still try to achieve a good loss and generalization, ideally. And the way they do that is that they decimate parameters near the end of training. Usually they pick the end of training, the trained parameter. And then they will decimate parameters based on the Fisher information matrix. So they will look for ones that are smaller than some given cutoff scale, capital lambda, and they'll like set them to 0 or resample from the prior, or there's probably other ways you could do it. Sorry, question? Nope. Sorry. So yeah, the parameters that are considered small scale, so ones that are smaller than this Fisher information diagonal entries, are removed from the model. And then coarse graining is like simply a projection map from your original parameter space to this pruned parameter space where you just remove all these parameters that you decide to not keep. And then after you do this decimation procedure, we then have a new expectation values and partition functions where we've set the small scale parameters to 0. And now the question is, if I was to compute the expansions of these new objects, what do I get? How much is preserved? Yep. Yep. Boop. Yeah, I think you're right. We're zeroing out the small parameters. So you can decompose your parameter space into small parameters and large parameters, and the ones that are considered small are set to 0. Yeah. Sorry, KOW was a Kullback-Leibler divergence, which is the measure of how good our model P was to the truth. Yeah. So if you've achieved KOW equals 0, then like you're at the end of training.
Any intuition on why the diagonal entries and not like after we actually diagonalize it?
Yes, good question. I think in some papers they don't bother diagonalizing it, like in the Howard paper from 2025, but usually we will be diagonalizing it with respect to the basis of our true parameter here to get like a meaningful scale. And the diagonal entries just simply because I'm actually not too confident. I would say it's just probably a simpler procedure than.
I think Roman has some argument about why this contains most of that.
Okay, yeah. Okay, so the main headline of today is that if you do this Bayesian renormalization procedure, you effectively destroy all the interesting singularity structure in your network in one coarse grading step, no matter how small you take. So the toy model we're going to consider is going to be an L-layer linear network without biases. So we've got a product of L matrices where each matrix is a HI by HI plus 1 matrix. And I'm just using the convention that the output layer is N and the input layer is M. So as I just said, for any cutoff greater than 0, the renormalization procedure collapses the model's asymptotic expansion from including polynomial and log terms to ones that just contain polynomial terms. And the leading order behavior of the partition function becomes the effective dimension space over 2, rather than the lambda I mentioned earlier, which can be actually strictly less than this. So this is maybe not what you would want. If you think singularities help you generalize, then maybe killing off all the singularity structure in one step is not ideal. So the expansions we just saw before, if we apply the Bayesian renormalization, is that now our expansions take this form here, where we no longer have any logarithmic terms in our expansion. And the leading order exponent, however, will be preserved, but not the leading order coefficient, and none of the sub-leading order terms or exponents will be preserved. So yeah, all non-trivial singularity structure is killed after one coarse graining step. So we're going to hopefully try to think of a way to maybe preserve that structure. But first, we're just going to look at some observables that, oh yeah.
Yeah, so if I may, I'm a little confused why you're talking about, like, we get rid of these parameters, and then this is like destroying the singularity structure, and that's going to harm generalization behavior.
Yep.
But my understanding is that, like, the coarse graining, by design, like, preserves that generalization observable. Like, you calculate the Gibbs? Am I wrong?
No, the Gibbs will not be the same.
It will not, okay.
No.
Why not?
Because you've set the Gibbs generalization error. So this is all this is about this toy model, for example. I'm not like confident in the general model, but for this toy model, if you set all those parameters to 0, then your Gibbs generalization error is proportional to lambda, and you've changed lambda from being what it was to being a different number that's the dimension space over 2 now. So you've changed the generalization error.
But as you take the cutoff to 0, does that approach that or no?
So the cutoff goes up in this case, because cutoff equals lambda equals 0 is keeping everything, and then you increase lambda, and you're carving off more parameters that way.
I think there's an order in the question here where you can, when you do a normalization, you have to commit to temperature. And the limit you're considering is the 0 temperature limit.
Yeah, that's right.
But when you do this renormalization step, you probably don't do it at 0 temperature, right? Or do you do it at 0 temperature?
Well, in the Berman paper, they do this at the trained network parameter.
Yeah, they do it at some finite temperature, right? But then there's no like. So I think maybe what you're saying, the way that you're reconciling the question, I think the question is correct. But like what you're saying is like we do this at some finite temperature, we get a new distribution that's treated now as a loss function, and now we want to look at that geometry, even though like now taking the temperature to 0 is not the same process because we're treating that we're normalizing. Right, where if you renormalize, renormalization doesn't commute with changing the temperature. Like if you first push water probability distribution and then raise everything to the second power, that's different from first raising everything to the second power, which is temperature by 2.
Okay.
And that's pushing forward. I think that's the issue.
Are you saying in this case the temperature is like the data set size? Is the temperature you're saying here like the data set size? Yeah. Yeah, that's true.
Yeah, I think that makes sense.
Yep. Okay, so we, as I mentioned before, would like, if we can, to still get the same macroscopic expectation values out of our renormalization step procedure. So given a true function, which is just the true parameter times x for a linear network, we can consider its singular value decomposition. And then we can break apart our network and true function into principal modes, which I'm going to note phi ij, with an orthonormal basis. And then we can define moments, which is the difference between our network parameter and the singular value that it's learning, or 0 if it's learning the 0 function. And then we want to consider expectation values of these moments. And these are like the natural observables that I would think you want to preserve under a renormalization scheme. And we can compute applying the main theorem from before, we can just compute the expansions for these directly, and we obtain the leading order is the expected decay rate of negative k on 2 when you've got a k-point correlation function. Am I going too fast? Any questions? Sorry, the delta is the difference between your network function parameter phi ij, which is the ijth entry of your parameter network in the SVD basis, and then you just take the difference between the singular value that it's learning. So it's like the fluctuation away from the singular value.
Are all of your linear layers aligned to the same basis?
Yep, that's right.
So you're looking at in the sacks.
Yeah, that's right. Now, it wouldn't be a talk on linear networks unless I mentioned saddle-to-saddle dynamics. So just for a quick connection there. So using that basis I wrote before, we can write the KL divergence as a sum of these phi ij quantities and then the singular values that we're learning. And then we can consider subsets that index which singular values we've learned. So Here, for example, J1 is the subset of parameter space that learns the first singular value. J2 is the subset that learns the first and the second singular value, and so on and so forth. And then you can define a stage-wise potential or a stage-wise Kähler divergence, which learns the first alpha singular values. And each of these will have their own partition function expansions and observables. And here's a quick experiment that I run, but you've probably all seen this plot before. So you've got this saddle dynamics in this black line going down, and then these potentials that we've defined here, these achieve minima once you've learnt the first singular value, first and second singular value, so on and so forth. So each plateau corresponds to a stage where a subset of modes have been learned. And now Bayesian renormalization is sort of truncating this hierarchy. As you raise capital lambda, you're sort of going backwards in training is the idea. So I've borrowed this picture from the Howard paper where they think of, at the end of training, you've got your cutoff is 0 and you've learnt the model. And then as you raise lambda, you're sort of truncating this hierarchy on this plot here. And the space of allowed models is going up, and you're sort of flowing towards the infrared. Cool. Okay, so we would like to not have such like a strong discontinuity, I think, in our renormalization procedure, where we have like all the singular structure at 0, and then I take one small step and it's all gone. So this is what we're going to work on right now. So I'm going to make two pretty strong assumptions to get this to work. The first one is I'm going to replace the negative log likelihood with population loss. Just makes the calculation, because we're going to be working towards trying to get a free field theory, and then we can talk about perturbations around this free theory.
Why is it so bad to just kill everything at 0?
Sorry, to kill the singular structure?
Yeah.
Yeah, so that's a good question. In a general model, so in the linear networks, after you do this SVD basis, it does push all the non-trivial singular structure into like the null space, like the 0 space, and then it does kill it all. In a general model, doing this procedure won't kill all the singular structure, but it will. But you'll have more complicated singular structure that's like, I guess, more spread out, which is like helping you learn maybe different parts of the network. And so, I guess to go back to my analogy at the start, if you drop down from having, say, S ways to learn something down to 1, I would say that's probably not ideal. But I agree in this particular toy model, maybe it's fine if you just care about learning the singular values that are in distribution. But if you want to generalize out of distribution, then maybe it's not so good.
And then on the second slide, so I like this idea of like time properties forward and things get more complex, and then you can run some procedure to boil things back down to their essence, and this suggests there's some like hierarchy and
Yep.
And then just like sounds some capability.
Mm-hmm.
One way that I sometimes think about doing this, although I haven't really like, either tried it or seen it explored, is like, yeah, training completion, and then gradually keep training, but gradually increase your weight decay. And then you'll sort of slowly unlearn everything until you end back at the origin. And you can imagine, like, I mean, I think in the deep linear case, you'll undo the saddles.
Yeah, I think so.
This is less, So this is kind of like inverse learning, kind of in the lower distribution. But I think Berman shows that like in some assumptions, this is the kind of the correct inverse learning in some kind of.
Yeah, I mean,
setting it is kind of.
yeah, I mean, I believe this is like mathematically nice. Also, the way hitting is way easier to do experimentally, and it's just like.
Both are pretty.
Cool. Sorry, do you have a question, Laura?
Yeah, I was just wondering if you have any, like your last experimental slide, did you, have you thought about generalization?
Yeah, I have a bit, but nothing that I feel confident enough to say in public. Maybe we can talk about it after the talk. I don't like saying things that I'm not like 100% sure is true. So the first assumption is maybe not so bad. The second one, we're going to replace the population loss with something called a comparable function. And just for a quick definition, comparable functions, f and g, are ones such that if I can sandwich either one above and below by the other function for some positive constants, C1 and C2. And this might seem like quite a big change, but doing this does preserve all the singularity structure and the asymptotic scale. And this is the main content that I personally am seeking to preserve with this procedure. And if you make these assumptions, then you've collapsed your linear network into a free field theory, provided you coarse grain via Bayesian renormalization. Because Bayesian renormalization kills all the singularity structure in one step, and then what's left is a free field theory. You can just like iteratively integrate out parameters at will. So, and what we get from this now is because we integrate out the parameters now instead of setting them to 0, then we actually get the, oops, oh dear. I did it again. Ignore the last point for a sec. But you actually get the same, the correct macroscopic observables. So I'm going to define this space of theories called T sub W, which is a model truth prior triple for a parameter W. And then the RG transformation I'm going to define is going to map from a space of theories from model truth prior with parameter W down to a model truth prior W greater. And then instead of setting the parameters that I don't want to 0, I'm going to integrate them out using the fact that I've now got a free field theory. Yes?
Why is W the index of set here? The triple PQE functions.
Why do I like denote T sub W?
Why do you denote T sub W, and why is there a given W?
Oh, do you mean over here?
No, first. The set, yeah. What is that doing?
That's a good point. I guess not a lot. I guess that's, yeah. It should, sorry, that doesn't look like.
The space is just like the space tree simplicities.
Yep,
Okay.
that's right.
The subscript W is saying I supported the same P is parameter.
Yep.
I see.
Uh,
Capital W is okay.
Inside T sub W, the capital W is not changing. But then we're projecting to a different space, which is the different capital W, because we're integrating out, we're getting a new parameter space. Okay, so just to define what your new triple is. So the large scale model, after you apply this procedure, is going to be the original one, just added that's projection map. So thank you, Edmund, for pointing out the incorrect notation here. But what this is meant to indicate is that you have your parameter space W, and then as before, you set all those parameters to 0 as before, but we're going to account for the asymptotics in a second. And then you do the same thing for your large scale truth. And then you can define a new Kähler divergence, which is the difference between your large scale model and your large scale truth. And I'm going to introduce a notation for the small scale, which is all the ij indices in my Kähler divergence from before. And then we can actually split up the Kähler divergence over this small scale parameters over here, and this, large scale parameters over here, and the small scales here. And so then my theory is going to factorize in the integral. So you start with the integral given here. Sorry, omega should be W there, that's a typo. And then after you pull out the minimizing point, then you can factorize all the stuff you want to compute the expansion of into these big square brackets. And then we're going to define that to be like a large prior, which is, I think of this as my original prior, but I've now integrated out my knowledge of the short scale parameters. And to account for this, the asymptotic scale, I can now compute this as an expansion using the previous theorems on the first few slides. And now I have a new effective theory for the large scale with this expansion being my new prior. And this is all in the large data limit, so I'm considering asymptotics as being reasonably close enough to the objects that I want. Okay, after all that work, we finally get there. So the comparable theory, so we've got this renormalization group transformation that maps from parameter spaces in TW to TW greater than, which gives us, it takes in a model truth prior and spits out the model truth prior I just defined. And then this procedure leaves all the expansions invariant as n goes to infinity. So in other words, I would like to say like these diagrams commute, meaning if you were to start with your model truth prior and just straight up compute the expansion of the expectation values or the partition function, that's the same thing as if you first renormalized and then computed the expansion. And so you can renormalize to your heart's content and keep computing expansions, of course, until you run out of parameters, because the parameter space is a compact set.
What changed here? So you replaced the loss with this kind of effective, kind of comparable thing.
Yeah, so I made the loss population first, and then I replaced it with a comparable function. And then in a sec on the conclusion slide, I'll talk about how you can sort of like use perturbation theory to get back to the original. But this gives me like a free field theory that I can now like expand around.
Yeah, so like, is it the correct notation that when you were normalized, you had some kind of, set of, it was some geometric structure that was a minima and now that broke, but now you've like modified the function to like make it align with your normalization correction.
Yep. Okay, so I know it's almost lunchtime, so we'll do a quick conclusion. So we demonstrated that the Bayesian renormalization transformation as it currently existed just killed all the singular structure in the model. And this fundamentally changed the asymptotic behavior of the observables and the partition function, and hence our free energy. So we can recover this asymptotic scale, but you do pay the price of needing to use comparability and population loss. But then to get back to the original theory, you probably can use perturbation theory because we can compute, using the theorem from the start of the talk, you can compute the whole expansions in one shot. That's not hard, but then computing it iteratively with RG is harder. And so we can do it in this comparable case, and then we can maybe use perturbation theory to do it in this around the comparable theory, and then see if these two expansions like match. I haven't done that yet, but that's potentially future work. And yeah, again, in more realistic models, I would not expect this to remove all the singular structure in a single step, because the singular structure in a more general model is a lot more complicated. It can't be so easily removed. And yeah, so how Bayesian renormalization affects the singular geometry in like the general cases is an open question. But at least in this toy model, I hope we've been able to say that SLT can say something interesting, at least, about how it currently exists if you do not want to take a large width limit and instead look at the large data limit. That's all I've got for today, so thank you. All right, questions?
Like in the PLN case, is it that you're pulling out all the singular structure because the singular structure comes from the data, because the degeneracy is from like the parameter function map? Like.
Sorry, I like when I remove all the gauge. So when I do this, you first like align your parameter to be the same basis as the SVD, and then when I say it removes all the singular structure, even if I like first remove all like the gauge symmetries myself, it kills all like the remaining singular structure, if that makes sense.
It's weird.
It is weird.
That's super strange.
Yeah.
Why is this strange? You're doing something like something that's very unstable, right? And then
Well, I think sort of what I'm getting at is that like you could in theory remove all this singular structure that comes from the data and preserve all the stuff that comes from the parameter function map in some weird way.
that's what he's doing, right?
Right? But this is what I'm saying in this case, like if
I
there's
see.
no degeneracy comes in. I think.
This is so maybe you're always working right in the kind of like in the infinite data but finite data setting, right? When you're doing formally.
Finite
Do you ever actually look at finite data?
finite data.
Like finite data in the sense of like you change the actual data set rather than changing data.
I guess I would say I work in the standard SLT regime where we compute asymptotic expansions in the dataset size.
But like if I were to take the infinite average over the infinite data set and multiply by data, all your results will still
Oh, yeah, can I have like an inverse temperature and like vary that?
Yeah, like, we'll
Yeah.
call it n, but like multiplied by n instead of like saying, oh, I just defined that, right?
I think as long as your model is still like converging around the singular locus as like the data increases, you can have an inverse temperature as long as it doesn't like ruin that.
No, I'm saying, like, n, the way that you use n, it multiplies by, like,
Yep, it works as
for formal linear formal models, it multiplies by the infinite data. Like,
Yep.
it multiplies by the true population model. Right?
Yep, that's right. Yep.
Okay, no more questions? Let's thank the speaker again.
Thank you.